Hello and welcome. My name is Aarti. I'm a serverless specialist SA for ASEAN. Today, my colleague Trin and I will take you through the best practices for developing serverless applications on AWS. For this talk, we will assume the audience is familiar with the basics of AWS Lambda and serverless. I will kick off with design principles for architecting modern serverless applications. I will then cover how to use workload characteristics to design integrations. Trin will explain the basics of events and wrap up with tips to optimize your AWS Lambda functions. A small detour first to understand the role of serverless in modern applications. Let's think about what the word modern means. Modern refers to something new and relevant today, like the latest fashion trends. What is modern today may not be modern in the future. If we extend this to the world of information systems, modern definitely means using new technologies such as containers, serverless, artificial intelligence, and more. But it is more than the technology. It is equally about process and people changes to adopt a new way to design, build, and run applications. So what exactly is this new way? So here are the principles of modern applications. From an architecture perspective, you work backwards from your business capabilities to build modular applications with each module aligned to a business domain. From a data perspective, it is important to think about data access and data dependencies upfront. From an operations perspective, offload as much as possible by using managed services so that you have more time for business logic. And finally, from an organizational perspective, platform teams take on the role of enablers by building capabilities and tools to accelerate builders on the team. Serverless applications already have the design principles built into them and hence make it easier to build modern architectures. So let's see how these principles can be applied. Let's start with architecture. Monolithic thinking means starting with the tech stack. Let's consider an e-commerce store. If you start with the tech stack first, you will end up with an inventory of services such as an application server, a database server, and so on. On the other hand, a product mindset forces you to think about key capabilities you have to offer. For an e-commerce store, you need to provide a great selection of products, fulfill orders, ship them on time, and so on. This domain-driven thinking naturally moves you towards a modular microservices architecture. Now, a modular architecture introduces new considerations. With microservices, state that was shared on a central database in a monolithic application is now distributed. Events are the connective tissue in serverless applications, allowing the modules to communicate with each other and exchange state. I will cover more about choosing integration services in the next section. Trin will revisit events later in the talk. On to the next principle. Choosing managed services offloads a lot of the operational responsibility to AWS. As an example, for AWS Lambda, AWS manages the underlying infrastructure and foundation services, the operating system, and the application platform. You are responsible only for the security of your code and permissions for your Lambda function. Now, the last principle. Get platform teams to focus on accelerating agility. Smooth those CI/CD pipelines, automate the account vending process, and create robust guardrails to reduce the blast radius of bad app behavior. Create reusable infrastructure as code patterns as building blocks to give your builders the runway to go faster but safely. Always think about how you can help and support without creating a bottleneck. As mentioned earlier, let's take a closer look at designing integrations. Integrating systems is not a new concept, and this slide shows a few different ways we have been traditionally doing this. However, what has changed is it's no longer about building applications and integrating them afterwards. Rather, integration is application and you need to consider it much earlier in the design lifecycle. You can compare integration approaches along different dimensions. For example, coupling tells you how closely the applications are dependent on each other. Asynchrony tells you whether the calling application expects a response in real time or not. Ordering impacts sequencing of messages, and delivery semantics has implications for idempotent processing. While there are other dimensions, these are the ones important to our discussion today. So how do we use these design properties to design integrations for our e-commerce store? Let's start with APIs, one of the popular ways to expose your microservices. REST APIs implement a synchronous integration pattern. This means the caller is blocked till it gets a response. This also means the components are more tightly coupled. You can use Amazon API Gateway to build REST APIs and AWS AppSync to build GraphQL APIs. GraphQL is an open source data query language and is an alternative to REST APIs. There are multiple use cases in our e-commerce store where we can apply the synchronous pattern. As an example, our checkout service makes a RESTful call to a third-party platform to verify payment. You do not want to approve the order till the payment goes through, and here we require a synchronous pattern. But not all integration patterns in our store need to be synchronous. For instance, while the fulfillment service needs to know the products that were checked out, there is no need to do this in real time when the customer checks out. Order fulfillment takes hours at best. In this case, the workload naturally lends itself to an asynchronous communication pattern. The degree of dependency between services results in two different patterns for integrating applications. These are referred to as choreography and orchestration. Choreography works well for decoupled application like the catalog and fulfillment service, where the flow of information is usually one way. There is generally no need to undo things upstream if something goes wrong downstream. You can use Amazon Event Bridge for choreography. On the other hand, when you have multiple components come together to fulfill a single transaction, it is important to undo previous steps when something goes wrong downstream. In such cases, you can simplify your application code by offloading the coordination to a separate service called the orchestrator. You can use AWS step functions for orchestration. Now, in both these cases, the event or request is pushed to the target service. In other words, the rate of invocation is determined by the rate at which events are produced. But as a consumer, you may not want to process events at the same rate that they are sent. Or maybe as a consumer, you're interested in a sequence of events rather than each individual event on its own. This is where event stores come in. Let's go back to the e-commerce store to understand where event stores can help. Let's say we run a big sale. Ordering service has to scale up to keep up with the sale traffic without sacrificing the SLA. It has to handle thousands of requests per second at peak. Now, our fulfillment service has to also process thousands of orders coming in, but it has a few hours to process each request. So the fulfillment service can use an event store to buffer events and consume at its own pace. You can use Amazon SQS or Amazon MQ on AWS to create queues. This is a one-to-one communication pattern. You can have multiple consumers, but each message is delivered to only one. In this case, order 2 is not available to other consumers as it is still being processed. It is up to the consumer to delete the message from the queue once processed successfully. So in this case, order 1 has been deleted. Now let's say we want to add machine learning based recommendations to our store. We can build a clickstream analytics service that makes real-time recommendations based on a continuous stream of clicks. This is time sensitive. Also, if we think about how we process this, while we care about the click that resulted in a purchase, we also care about all the clicks the user did before they actually bought the product. In other words, we are interested in a time window, typically the user session, rather than individual click events. In such a case, a streaming data store such as Amazon Kinesis or Apache Kafka works best. Here, the same data stream can be consumed by multiple subscribers, each keeping track of where it is in the stream. Data is not deleted until it expires. Finally, sequencing an exact once delivery is important in this use case. Now, although I called out services for each use case, please note that some services are capable of supporting multiple use cases. Working backwards from the workload needs will help scope your choice. The actual choice will come down to other factors such as in-house skills to use the service, organizational mandate for open source, and cost. Now that concludes our section on choosing integration services. Over to you, Trin.
Thanks, Arthi. Hello, my name is Trin, and I am a solutions architect at AWS Vietnam. As we have heard Arthi explain about different integration patterns and how events are connective tissues in serverless applications. Now, let's dive into the event itself, looking at what information we should include in communicating between different services. The definition that we often associate with an event is, it is a signal for when a state has changed. But we can also define it as a contract for integration. This definition supports the design principle that Arthi has mentioned with thinking about the business capabilities and how they connect. An event, therefore, must be established on a level of trust between the producers and consumers. This leads to the final definition of an event, that it is an immutable object. If an event is modified before it is consumed, it is no longer the same event. As we had different ways of defining an event, we also have different types of events. By understanding the different types of events allows us to recognize where and when to apply them in different integration patterns. Firstly, notification events. As the name suggests, they are basically signals, notifying consumers that a state has changed or something important has happened. These events typically have minimal information. Therefore, the event consumer may need to query the producer for additional context. For instance, notifying when an order status has been changed in the notification service. Next, we have event carried state transfer events. These are events that capture change in data, which eliminates the needs for consumer to call back to the producer for additional data upon event consumption. For example, DynamoDB Streams event is an event carried state transfer, as it includes the delta changes made to the items in your table. Putting the example into our e-commerce store, these events could be used to carry new order details from the checkout service to the order service. Finally, we have the domain event, which is the combination of both. Domain events capture all the context necessary for the service within the same domain. Let's look at an example of a domain event, which is an event bridge event. With an event bridge event, we have the envelope with the information about the event itself and the detail field where you provide the additional context of the domain. First, the event should include some metadata, such as a correlation ID. This correlation ID can be useful for tracing an order or be used as an idempotency token. Next, we have the detailed data where we provide the context. Here, for example, we have the ordered ID and additional details about the order for the consumer service. If it was a notification event, given only the order ID, the consumer would need to query the producer for additional details on the order. Similar to the order details, we also include information about the user requesting the order, therefore providing all the information about the domain. The state captured in the event allows the downstream service to build up its own cache of data that it can enrich and send on. When designing an event content, we must consider whether we are providing enough details for the downstream service without unintentionally exposing implementation details. For example, the order details, what the amount is ambiguous, or the delivery address is not fully written. Moreover, we must consider the PII information that we are including in the event, whether we would want the downstream service to see this information. As we have mentioned a lot about event-driven architecture, we must understand that it uses asynchronous communication via events. We often see the use of Lambda in event-driven architecture and mistaken that Lambda is event-driven, but it is actually event-based. What does event-based mean exactly? Event-based means that the existence of a compute instance, here a Lambda function, is intimately tied to the occurrence of an event to be processed, once at a time. Next, we are going to walk through how we can optimize Lambda functions given that it is event-based. I will walk you through how Lambda functions concurrency and codas work, as well as how we can optimize Lambda functions for performance improvements, and showing an example of using Lambda codas in our e-commerce website. Lambda functions run in an execution environment or sandbox that is dedicated to the function. As I have mentioned that Lambda function is an event-based compute, each sandbox, therefore, only processes a single event at a time. There are three phases in an execution environment lifecycle: the initialization phase, which we call the code start, the invoke phase, and the shutdown phase that is not shown here. When a request comes in for the first invoke, Lambda runs the first part of the init process, which downloads the code and all the layers, or your container image, for the function and initializes the runtime. It then runs the function's initialization code, which is the code outside the main handler of your function. The invoke phase starts when Lambda runs the function handler code, which receives the event payload and processes your business logic. When the invoke phase is complete, the sandbox remains warm to run function handler code again. The count of the in-use sandbox at any point in time is what we call concurrency. Understanding how Lambda functions concurrency works allows us to effectively choose the right mechanisms to optimize your functions. So following the timeline, when a request comes in, Lambda runs the initialization process, which creates the sandbox based on your function configuration. Then it invokes the function. This is a code start. And it continues to create other sandbox as requests come in until the function code finishes running. Then the free sandbox can handle another request. This request then has a warm start, as you can see with request number 6. As the process continues for subsequent requests, you can count concurrency as the number of parallel requests. In this diagram, you can see how concurrency fluctuates as requests come in and execution environments are being created and reused. The metric concurrent execution is available on CloudWatch for you to observe concurrency of all or individual functions. So how does concurrency relate to transactions per second? The number of transactions Lambda can process per second is the sum of all invokes for that period. If a function takes 1 second to run and 10 invokes happen concurrently, Lambda creates 10 sandbox. In this case, Lambda processes 10 requests per second. But if we optimize the function, halving the duration to 500 milliseconds, the Lambda concurrency remains 10, however, they are being reused within the seconds. Therefore, transactions per second increase to 20. There are two types of concurrency that you can provide with your Lambda functions. You can use reserved concurrency to allocate a maximum concurrency limit for a given function. A maximum number of requests a function can run in parallel. This reserves concurrency for a particular function from your account's quota. One use case for using reserved concurrency is to protect downstream resources. If a database or external API can only handle 50 concurrent connections, you can ensure your Lambda function cannot scale beyond 50 concurrent invokes and overwhelm the downstream service. The other control is provision concurrency, which allows you to set the minimum number of available sandbox in advance. In effect, running the cold start process beforehand, allowing your functions to be invoked immediately when the requests come. We have mentioned that reserved concurrency is allocating concurrency for the particular function from your account's quota. It's important that we understand the different types of Lambda scaling quotas. The burst concurrency quota gives you an initial burst of traffic for each function between 500 and 3,000 per minute, depending on the region. After this initial burst, function can scale by another 500 instances per minute. There's also an account concurrency quota, which is the maximum concurrency in a particular region. This is shared between all functions in an account in that region. This defaults at 1,000 and can be easily braced with service requests. Let's go back to our e-commerce store, and let's say we're running a big sale with the next day delivery, expecting the application to handle thousands of requests per second at peak. Expecting a large spike in traffic, the application builders have raised the default account concurrency quota from 1,000 to 7,000, as you see marked with the green line here. And with no other functions in this account, this function can use up all the available account concurrency. The burst concurrency available in this region is 3,000. Just before 9 a.m., the application has a steady stream of requests utilizing 1,000 concurrent sandbox environment, with the burst quota available for 3,000 requests. At 9 a.m., the sale begins. There's a large spike in traffic with 5,000 requests, in which 1,000 requests use the existing execution environments with warm starts. Lambda then used up the 3,000 available burst quota to create new environments. The rest 1,000 requests are throttled, as there is not enough burst concurrency available. In the next minute, Lambda scales by another 500 concurrent invokes per minute, as the burst concurrency is used up, and 500 requests are still throttled. Lambda scales by another 500 concurrent invokes per minute. Now no request is throttled. The application can now handle all 5,000 requests. And the app continues to handle the sustained 5,000 requests, and the burst concurrency quota rises up to 500. At 4 minutes past the hour, the application gets another spike in traffic, an additional 3,000 requests, making it a total of 8,000 requests. So let's break it down. 5,000 requests can continue to use the existing execution environments. An additional 1,000 burst concurrency is now available for use. 1,000 requests are throttled, as there is not enough burst concurrency. Another 1,000 requests are throttled, as the account concurrency quota has been reached. As the burst concurrency increases by 500 every minute, it will fill up for the request until it reaches the 7,000 request quota set by the account quota. Hence, 1,000 requests will remain throttled by the account quota. So now that we have seen how concurrency and quotas work, we can see that with a faster Lambda function and concurrency, you can optimize your transactions per second. So how do we optimize Lambda functions? Back to the Lambda execution environment lifecycle. With this lifecycle, AWS can optimize the part of running the service, and you can optimize your code. If you're using a standard function configuration, your optimization starts at the function pre-handler code. However, you can use cool Lambda functions like extensions or runtime modifications to control part of how Lambda works, and so your optimization shifts left in the timeline, where you can control the extensions code and how the runtime starts up. This means you have more authority in optimizing your Lambda functions. So what can you do to optimize your part of the Lambda function, and what best practice should you think of? Firstly, don't load it if you don't need it. Optimize loading any dependencies to only the modules. Reduce the deployment package size, which can speed up code starts. Pre-handler code is great for establishing connections, but be prepared to then handle reconnections in further warm invokes. For instance, establishing connections to your database or other AWS service that you need to perform your business logic. But it's important to understand that the execution environment will be reused, and so is your pre-handler code. You can store state for subsequent invokes, but conversely, make sure you're not storing any data or secrets you don't want subsequent invokes to see. Linking back to what we have mentioned before, if you need to banish code starts, use provision concurrency. It does not require any code change. As we mentioned that you can optimize loading dependencies to reduce code start duration, sometimes it can be convenient to load the whole AWS SDK package. But if you are only using DynamoDB in your code, by loading only the DynamoDB SDK, it can be 125 milliseconds faster. Similarly, for X-Ray, by adding -core to the package name parameter in require, saved 5 milliseconds. Especially for X-Ray, if we become more specific with the reference, for instance, when using document client, it saved up to 140 milliseconds. Being more specific means the code references a smaller package, and it can be faster to initialize during the code start. To recap, you can start designing modular applications by having a product mindset and focusing on your business domains. By understanding how the different domains in your business interact, you can implement the right integrations between the service. And by understanding how Lambda concurrency and codas work, you can start to optimize your code for performance improvements. Thanks very much for your time. I hope this helped clarify a little bit more about how AWS Lambda works. And now, I'll hand it back to you, Arthi.
Thanks, Trin. So here are some useful resources to explore some of the concepts we discussed in greater depth. Check out our serverless ramp-up guides to gain a deeper understanding of serverless on AWS. You can validate your knowledge of serverless by earning a digital badge. For plenty more general serverless information, head over to serverlessland.com with lots of resources about all things serverless. Visit Skill Builder, our online center, and explore over 600 free digital courses, hands-on labs, and role-based games. For teams and individuals looking to dive deeper, Skill Builder subscriptions provides access to premium content and administrative benefits. And when you're ready, discover industry-recognized AWS certifications that showcase your expertise and grow your career potential. Trin and I would like to thank you for your time today. Please take a minute to complete the session feedback.